Hey, Mark, thanks for having me on the show. Yes, Bruce Sinclair, technologist, business person, and investor. I've been in technology. Well, that's pretty much all I've been in. So when I first got out of school, it's been tech, and that's even when people really didn't even know what high tech was.
What did
But
you
thanks for
study in
having me.
school, Bruce?
Uh, well, yeah. Originally I thought I was going to be an engineer, and then I kind of flunked out of. So the irony is, I flunked out of my computer science class, and then computer science ended up being my career. But no, I ended up flunking out of that because I was in a high school where there was no computers, and
Hmm.
just the concept that for people that have actually programmed, the concept of programming actually just takes a mind. It just takes a bit of a mind shift. But in any case, my undergraduate degree is in mathematics, so I'm a mathematician. Yeah.
There you go. You know, Bruce, you and I, when I'm thinking back in the day, we were part of our business was helping game designers create these incredible environments to be able to, immerse people in the games. And we literally were at the very beginning of all of that. And you were
Yeah.
leading the charge in all of that. And my question for you is now looking back 30 years later and the kind of the it was the I think the goal and dreams of designers at the time were to create these fantastical worlds, and your job was to kind of help be the bridge between them and our engineering team to be able to
Right.
create the tools they needed. Tell us just a little bit about what it was like then, but what you've seen change over the past 30 years. I mean, it's been seismic.
Yeah, no, I mean, so in particular, when we talk about gaming are perfect examples of virtual worlds. Originally, when we started gaming, we were working on the flat Earth, in the sense that it was 2D. And if you remember, one of my favorite games was Defender, and then it kind of went to 2.5D, where you got this oblique angle. But what we were doing at Wavefront was the product was activation, and we were helping developers first with gameware and then activation, but we're helping developers build these three-dimensional worlds and then navigate within them and just give them tools for how to create the worlds, and then how to create the objects in the worlds, how to create the characters in the world, and then how to have them all interact together. So at a fundamental level, how it all works, and now we got the metaverse, which I know you've had on your show, you've been speaking about on your show before, but really it's the same. It's the same thing. So what hasn't changed are all the fundamentals for how this is all done mathematically, and how this is done programmatically. It didn't change, So I can't believe it was 30 years ago, but yeah, I guess it was 30 years ago.
I did the
Well, the math
math.
that we're using is probably, some of it's 3,000 years old, some of it's 300 years old, and some of it is obviously 30 years old. That part hasn't changed. What really has changed has been a couple of things. Back then, the internet was very early stage, and so the environments, when you had more than one person within an environment, or was one person in a computer, then they had to be connected directly. Now obviously we're doing it over the internet, so the technology for sending information and just the networking technology itself has changed. And then the secondly has been the rendering. So for people listening, there's kind of three stages in computer graphics and in the metaverse. The first stage is making the objects. The second stage is to animate the objects. And now these animated objects can be done with a joystick. It can be done by an artificial intelligence algorithm. And then the third is the rendering. And the rendering is really just the coloring. And so, whether you're looking at a flat screen like I did at Defender, or flat screen when we started getting into 3D games, or even a VR headset where you could then look in the environment in all different ways, the rendering really is really what has changed a lot in terms of making it more and more photorealistic, so that you feel that you're in the environment. I don't know if you heard the term the Uncanny Valley.
Yeah, I have. Explain that to our audience.
Yeah, so the Uncanny Valley is when it's almost there, where you're looking at a synthetic environment, or generally environments are a lot easier to do this. Well, not generally. Environments are a lot easier to do this because they're static. When we start looking at humans, it's something about our primal conditioning that our brain zooms in, and we kind of can figure it out whether that's a real human or whether that's a, you know, a fake human. And when it's super close to being real, then it's a little bit uncanny, but it's not quite there. So we are not quite there yet. But the rendering technologies, and then, you know, what's underneath the rendering technologies is changing too. But I would say that would be the area that has really changed a lot. If you remember, Mark, we used to have these big old refrigerators, and I'm talking about not the beer refrigerators. I'm talking about the walk-in, almost the walk-in refrigerators. These Onyx machines. The Onyx machines, they cost, remind me, about 100 grand, 150 grand.
They were 250, 275.
You would remember, yeah. So like 250 grand, and I believe the Onyx machine had less power than this baby here.
It did.
And specifically, even on the graphic side of things. So you got more computation. That's important, but yeah, the visual representation is what's really advanced. But the real basics, have pretty much stayed the same.
So I think there's this other. I'm going to add a fourth dimension here, which is the intelligence that we add to these things. Absolutely, right? Yeah. So, you know, you can build it, and then you can animate it, and you can light it, but the intelligence that lets these objects communicate with one another, both in an environment or in a manufacturing plant or wherever, that's all new. Why don't you tell us a little bit about where we're at in that, in terms of the intelligence of these objects?
So if we go back to the Defender game, I'm hoping people understand what that was, but it was like a shooting game. The intelligence was there too. It just wasn't super intelligent. And so, you know, if you would move and you would shoot, and then the other spacecraft would move and shoot at you, and you'd maybe dodge. So you're playing against a computer algorithm. In those cases, the computer algorithms were deterministic, meaning that they are still now, but meaning that you kind of literally programmed what they would do. If Bruce moves up here and you're in this position, you do this. And now the advent of what really changes has been artificial intelligence, and it's specifically machine learning. Artificial intelligence can actually, there's a lot of different forms of it, but machine learning and in specifically adversarial machine learning, where you use it in games such as chess, but you can also use it in these 3D environments. So instead of moving these other characters with a joystick, the artificial intelligence, which really is just a fancy way of just saying software, we do the same thing. If you remember, we wrote code, we compiled it with libraries. We take these Silicon Graphics libraries, we compile them into our software, and then we'd execute it. Same thing with artificial intelligence. All they are is a bunch of libraries, and then you compile them in. But the difference is that they can learn. And when I say learn, it's not really learning, but it's that they can replicate what they see, and they can make decisions. And adversarial artificial intelligence eventually is an algorithm where you win and lose, and when you start winning, you start learning what you do to win. And so that is really the biggest advance, is when back in the day, when it was Defender or Stargate, which was the next one up, you know, the intelligence was actually just, they weren't that smart. You know, their IQ is pretty low, but now the intelligence has gone up quite a bit. But interestingly enough, you know, like my son, who's now graduated and so forth from university, but really the games that have the most impact are when he's playing with his buddies. And so even now, you know, when we look at the sophistication of that Defender or Stargate character, it was good. And now we look at what we have now, and it's like super good compared to that. But still, it's kind of like not even close to that Uncanny Valley. So the Uncanny Valley, as we were speaking about earlier, was just actually trying to recreate the looks of something. When you have software that's trying to recreate the brains of something, it's so far away. And so there's still, you know, so still even today, even though that has advanced so much more than it was 30 years ago, people still like playing against people because they're smarter. They're still smarter than the AI.
What's interesting is, to me, is that the technological advances that have happened in games, both on the latency, so things happen quickly, the ability to do it over tens of thousands of people, to be able to do it on relatively inexpensive computers, that has paved the way for this technology to be adopted in other environments. So this idea of digital twins is to be able to create a digital twin, for instance, of a manufacturing plant, right? So we've got my real manufacturing plant, or the one I like is at Amazon, right? How do you pick and pack the stuff? How do I get my things the next day? And when
Right.
you look at how they have designed the robots to be smart, because they have cameras that are trained on what to look for, right? To your point, right there, there's libraries of here, this package looks like this, et cetera, et cetera.
Yeah.
And they can take in the ability to build a digital environment that's exactly what the real world warehouse is like. To me, that's a spectacular application, but it's built on the same techniques that you and I have been
Exactly.
talking about.
It's exactly the same techniques. And so the digital twin concept, you and I, back in the day, that was a visual representation. And so when we looked at something, we go, oh, okay, so there's simulating, and there's the first use of that word I think we've used yet. It's a simulation of the way someone looks. Now, digital twin, if you broaden the definition of the way it's used today, it still includes, how it looks, but it also includes how it moves. So then that's, remember kinetics, and
Yep.
kinematics. And
Yep.
so then you can include that, how it moves, but then how it thinks. And very narrow intelligence, what you're describing, you can have a digital twin of a human, maybe it's going to be a soldier. You can have a digital twin of a warehouse. You can have a digital twin of a manufacturing, but really it is how it thinks. And in my business today, I'm thinking about not necessarily how it looks and not necessarily to pack things, but how it would create value for a business. And so these digital twins are simulations, and the ones that we're used to is a simulation of visual simulation, but it could be a simulation in the warehouse is how to minimize the time to gather the objects to send them away. Well, that's a certain type of intelligence, but it's also about value creation. And then in the manufacturing plant, it could be how do we organize the machines in such a way that we have a faster output. Like I worked with a can manufacturing company. So how do we, and they would shoot out 60 of these per second. So how do we do that? So in both those cases, they're digital twins, but we can bring that back to the metaverse. And these objects now, when you're walking up to a street light, maybe it's triggered, or you're walking up to a car and how it behaves. These are all different examples of digital twins. And autonomous vehicles in driving within environments is another example where you're using a synthetic environment, often to train the artificial intelligence for the machine learning of the car, and then you endow these environments, and you endow the inanimate and the animate objects within that environment with some form of intelligence. And the digital twin encompasses all that.
I'm not gonna project the answer on you, but when you think about let's say the next 10, 20 years, right? Do you have a utopian view of the technology, or do you have a dystopian view of the technology?
I have a utopian view. I believe that as a mathematician originally, and as a programmer, and that was the irony of failing my computer science class, I know, and even with artificial intelligence, although there's something they call explainable artificial intelligence and unexplainable artificial intelligence. But in any case, it's an algorithm, and there's step by step, it does certain things. And so, as a programmer, you will know how it works. And so the concept is really the area where things can go awry are in unintended consequences, where the unintended consequences of maybe situations where you haven't thought through. But I believe as a programmer that you can put fail safes within the software itself that would prevent it from getting out of control, and the software getting out of control. A simple example is I don't know if you've ever heard of the paperclip thought experiment. So the paperclip thought experiment is kind of like that manufacturing digital twin we were talking about earlier. You teach us this manufacturing plant this robot, this whole group of robots in manufacturing plants to be the most efficient paperclip making machines possible. And what the dystopians worry about is the unintended consequence. And the unintended consequence is they become so good at it that they mine the entire earth from its natural resources. And you know what? The humans are a little bit in the way. They're a little bit in the way for us to make a buttload of these paper clips. And so it might just be a good idea to let's get rid of those humans. But we're going to focus on, making lots of paper clips. So that is that's maybe kind of a satirical example, but that really does bring together the problem. And that's the unintended consequence in terms of you're always going to be maximizing in a very simple artificial intelligence piece of software. You have a goal that you're maximizing for, but you could see in that paperclip example Asimov's 5 laws, where the robot laws, or they're still applicable today. And that's the interesting thing. I look at my bookcase there, and I'm kind of I keep just a few science fiction books, but just you were asking me the question earlier of 30 years ago, what has changed? Well, the 30 years before that, the thinking was the same, but they didn't even have those $250,000 refrigerators, but the thinking was the same. And so there's things even that go back as far as the 1950s with Asimov in terms of what he was thinking. These are the type of things that I believe you'll codify into code to prevent these unintended consequences, which is the existential disasters that everyone's
Bruce, you've given us a lot to think about. I'm going to get in my time machine, and we'll have another interview in 30 years, and then we'll see how much of this came true.
I appreciate it, Mark. That was a lot of fun and good to talk to you.